Section 21.15, Transitions in Metal-Metal Bonded Systems. What is a metal-metal bonded system? If you have a transition metal complex that contains at least two transition metal centers and they are directly bonded to each other, then it's a metal-metal bonded system with a metal-metal bond. In this kind of systems, we may observe photon-induced delta to delta star transition. So first, what is this delta? This delta stands for a delta bonding orbital. This is a delta bonding orbital. It's formed by the constructive interference between two d orbitals. So these two d orbitals are parallel to each other. And if you look at the positions of their lobes, you can see these two can interfere with each other in a constructive manner. Constructive interference between these two. Constructive interference. And finally, these two silver behind, can also interfere with each other in a constructive manner. And therefore, this is constructive interference between the two d orbitals, and this is a delta bonding orbital. So what is this delta star? It's delta star antibonding orbital. You just need to rotate this orbital 90 degrees so that this is going to be silver, red. And then when these two are close to each other, you have a nodal plane in the middle. Silver, red, silver, red, silver. Again, there's a nodal plane in the middle. This is going to be the third nodal plane in this orbital. Why? Because this d orbital has two nodal planes. Okay, both contain this center. This one also has two nodal planes. Both contain this transition metal center. When they form this delta bonding orbital, it keeps the two nodal planes. And both nodal planes contain both transition metal centers. All right? They both also contain the bonding axis between the transition metal centers. Now, if you look at delta star, all right, there's going to be a third nodal plane between the two transition metal centers. The third nodal plane does not contain either of these two centers. The third nodal plane is perpendicular to the bonding axis. All right? Now let me show you a real example of the delta bond in this transition metal complex. It contains two transition metal centers, molybdenum. These two are 4D transition metal centers. In this case, we have a quintuple bond between these two transition metal centers. Quintuple bond, it's rare, but it can be observed in the metal-metal bonded system. So now let me explain this. Let me show you a molecular orbital diagram to demonstrate that it's possible to form a quintuple bond between two transition metal centers. The MO diagram is right here. Okay, energy and atomic orbitals on the left, atomic orbitals on the right, and then we have just metal 1, metal 2. Well, they can be any 3D metals, and it's possible to form 5 bonds between these two transition metal centers. Among these 5 bonds, one is sigma bond, and you have 2 pi bonds, and then you have 2 delta bonds. Correspondingly, you have sigma star, you have 2 pi stars, and then you have 2 delta stars. If the two transition metal centers are identical to each other, all right, for example, well, let's say we have 2 iron 3 plus, okay, iron 3 plus, iron 3 plus, okay, these 2 orbitals are degenerate. These 2 delta orbitals are degenerate. These 2 pi star are degenerate. These 2 delta star are also degenerate. So how can we form 5 bonds between 2 iron 3 transition metal centers? Remember, iron has a 4s2 3d6 electron configuration in a neutral or iron atom. But now we're looking at iron 3, so its electron configuration is 3d5. You have 5 electrons here and 5 electrons here. Now let's look at the interaction between the atomic orbitals. Imagine this axis is the z-axis, all right? This is the z-axis. Now let's imagine you have a z orbital, dz squared orbital, okay? This is dz squared orbital on the left, another dz squared orbital on the right. Okay, they are pointing toward each other, and that's a sigma bond. That's a sigma bond. In a sigma bond, there's 0 nodal surface that contains the bonding axis. Okay, now let's imagine we have a dyz orbital here, dyz. So I'm drawing the 4 lobes here. Okay, this is dyz. Okay, you have a lobe here, a lobe here, a lobe here, and another lobe here. And you draw another dyz orbital here. All right, one here, one here, one here, one here, 4 lobes. And now, if this lobe is positive, this lobe is positive, constructive. This lobe is gotta be negative. This one is gotta be negative. All right, because if you have a dyz orbital, it's gonna be positive, positive, and then negative, negative. All right, so constructive interference here, constructive interference here. All right, and then in this case, you have one nodal plane that contains this bonding axis. All right, so you have one nodal plane that cut this pi orbital into 2 halves. You get a positive, positive on top of this nodal plane. You have negative, negative below this nodal plane. That's a pi orbital. Of course, if you use dyz to form a pi orbital, you can also use dxz and dxz to form a second pi orbital. So that's why you have 2 degenerate pi orbitals here. All right? And this dxz orbital is perpendicular to your screen. This one is also perpendicular to your screen. Finally, delta bonding orbitals. Now you need to imagine. There's okay, I said something wrong about the dxz interaction. When you have dxz interaction, you need to have the 4 lobes, 2 pointing toward the other metal and 2 pointing away from the other metal. Okay, so only 2 of the 4 lobes will interact with also 2 of the 4 lobes centered on the other metal. So that's the other pi bond between dxz and dxz. All right. So now again, let me emphasize this. This bonding axis is in the z-axis. This is your z-axis. So now let's imagine a dxy orbital that's perpendicular to your screen. Okay, dxy. Over here, there's another dxy. So this dxy and this dxy can interact with each other in a constructive manner to form a delta bond. All right? Delta bond. What about the second delta bond? Well, you have dx squared minus y squared, also perpendicular to the screen. Another dx squared minus y squared, also perpendicular to the screen. So these 2, both dx squared minus y squared, may interact with each other with overlap between these 4 lobes on the left and the 4 lobes on the right simultaneously. That's your second delta bond. So again, in summary, this is dz squared interaction. And then over here, dyz, dyz. dyz, dyz. dxz, dxz. So in this 2 pi bonding orbitals, there is overlap between 2 lobes on the left and 2 lobes on the right. What about the other 2 lobes? Okay, the other 2 lobes do not take part in this bonding orbital or antibonding orbital. And finally, 2 delta bonding orbitals. Okay, one between dxy and dxy. The other between dx squared minus y squared and dx squared minus y squared, centered on a second metal. And again, I'll let you picture the shapes of the antibonding orbitals. There are also 5 antibonding orbitals. Again, this is LCAO, linear combination of atomic orbitals. We start from a total of 10 atomic orbitals. We end up with 10 molecular orbitals. We have 5 bonding orbitals and 5 antibonding orbitals. And since we're talking about iron 3, and then over here we have 5 d electrons, another 5 d electrons, a total of 10 electrons, all occupy this bonding orbitals. In this sense, we say these 2 transition metal centers form a quintuple bond. The nature of this quintuple bond is 1 sigma bond between dz squared and dz squared. This pi bond between dyz and dyz. This pi bond between dxz and dxz. This delta between dxy and dxy. This delta bond between dx squared minus y squared and dx squared minus y squared.